Hello students, welcome to this lecture on the CMOS latch design part 2. So in this particular design, we will have a look, initially we will have a look into the Tristate inverter and how it is closely matching with that of the inverted buffer design. And the Tristate inverter will use it in the feedback part of the latch design so as to overcome the dynamic node output voltage, which was kind of which remained to be floating, and during an opaque state, it due to the subthreshold leakage current, it can get dropped and change the output node voltage, right? So in that sense, the tri-state inverter design is kind of very important to understand, and then try to use that in the feedback path so that we can have a staticized output node instead of a dynamic or a floating node output voltage. Right. So moving ahead, let's have a close look at the inverted buffer. So the inverted buffer design, we have an inverter here followed by the transmission gates. The clock is provided to the NMOS gate, and then complement of the clock signal is provided to the PMOS gate. Right. To look at the, to understand the difference between the inverted buffer and that of a tri-state inverter design, we need to understand the stick diagrams, right? In fact, to understand the differences or the similarities of the inverted buffer with that of the tri-state inverter, we'll have to understand the stick diagrams, and that's why the stick diagrams have drawn here on the right side. So if I want to draw the stick diagram of this particular circuit, which is an inverter followed by the transmission gate, we'll try to do it in a sequence. So try to draw the stick diagram of an inverter. So the inverter stick diagram is given by the P diffusion line and an N diffusion line. Also I have a VDD rail and then a ground rail, and we will have the D input here, which is separating the two diffusions on the P diffusion line and then two diffusions on the N diffusion line. The inverter, one diffusion line goes to the VDD on the P diffusion line, and then the another diffusion on the N diffusion line goes to the ground. The other side is the output node, which is nothing but the X output of the inverter. So this X output, which gets connected by a metal line. So this completes my inverter stick diagram. Followed that with a transmission gate. So the transmission gate, we will have phi bar given as an polysilicon gate onto the P diffusion line, and phi as a polysilicon gate applied on the N diffusion line. So I have a phi signal and then a phi bar signal separating the diffusion pockets of the transistor. So for an NMOS transistor, we will have the phi polysilicon gate, and on one side it is the X node and the other side it is the Q bar signal. So this is the Q bar signal, and on one side it is the X node. The PMOS transistor here of the transmission gate, which sees a polysilicon gate of phi bar and then separates out the diffusions of X and then the phi, X in one side and then Q bar on the other side here. So we will have this Q bar. So remember that this Q bar, which is nothing but the diffusion of the NMOS side and then the diffusion on the PMOS side, has to be connected, and that is being connected by a metal line in the stick diagram. So this is my input for this particular circuit design, which is nothing but an inverted buffer. So this is the input, and then this is the Q bar output, right? So this is the overall stick diagram of the inverted buffer. Let's have a look into the tri-state inverter. The tri-state inverter, we should have, the pull-down circuit as well as the pull-up circuit are nothing but the mirror image or a mirror topology, what we call or refer to. So I will have the D input given to the transistors which are closer to the VDD and the ground rails, and the other two transistors which are closer to the output node is supplied with the clock signal phi and phi bar. In fact, it's it is kind of symbolized with the help of an inverter kind of a symbol. But inverter is nothing but we have an output here which is bubbled. Instead of that, for a tri-state inverter, the bubble comes onto the input side, and the clock signal, because it's a tri-state, we have we in fact have two pair of signals. One is the input signal, the other one is the clock signal. So the clock signal phi and phi bar is also inherited in the symbol of the in the symbol design. right? So a tri-state inverter is kind of represented by this particular symbol where we have the bubbled input and then the clock and then the output, right? So remember that the output is Q bar, the input is D, and the clock supplied to the NMOS is phi, the clock supplied to the PMOS is phi bar, and that's why we have this bubbled input which is going to the phi bar, representing that this is this represents the PMOS transistor and this represents the NMOS transistor. Okay, so coming back to this particular the schematic in terms of the transistor level schematic, and then trying to draw that on a stick diagram. So we have 4 transistors, so the 4 transistors have to come, so that means I need to have 2 transistors on the PMOS side and then 2 transistors on the NMOS side. So 2 transistors has to be visualized on the stick diagram on the P diffusion line, and then 2 transistors has to be visualized on the NMOS diffusion line, right? So if I consider this particular transistor and this particular transistor, I should have an input signal of D, that means a polysilicon gate of D, which is cutting the P diffusion line into 2 diffusion pockets and cutting the N diffusion line into 2 diffusion pockets. On so this particular diffusion pocket is going to the VDD rail, and then this particular diffusion pocket on the N diffusion should go to the ground, and that's what is happening here and here. The other one is this diffusion pocket X1 and X2. So I just left it as X1 and X2 here. Phi bar polysilicon gate applied on the P diffusion line will create 2 diffusion pockets X1 and Q bar. So phi bar is cutting the P diffusion line into X1 and Q bar. So this is Q bar. And similarly, phi polysilicon gate is going to cut the NMOS or rather N diffusion line into 2 diffusion pockets of Q bar and X2. So Q bar here and X2 here. Right, so this is the stick diagram of the tri-state inverter. Right, so looking at the inverted buffer and the tri-state inverter stick diagrams, and if I actually put it nearby, we can clearly see that there is only one metal line difference. Right, there is only one metal line difference. Everything else remains the same in the stick diagram. Right, so X and X are connected. Here X1 and X2 are not connected. And if I connect this particular stick diagram, in fact, if I draw the stick diagram of a tri-state inverter and then connect this to nodes or the diffusion points into a metal through a metal line, then I actually get the inverted buffer design. Right, so the layout of the inverted buffer shows that it resembles very, very closely to that of the tri-state inverter with the connected X1 and X2 line. So what it really means is, in terms of the stick diagram, or rather in terms of the schematic, the inverted buffer, right, I can actually draw the inverted buffer using the tri-state schematic by connecting this X1 and X2, right, by connecting or wiring or shorting it, the X1 and X2 nodes, and now after shorting it, I'm calling it as an X node. So the inverted buffer schematic is nothing but the tri-state inverter design with these 2 nodes shorted. Right, now if I have these 2 nodes shorted, what is the advantage we have? Now whether we have an advantage in the inverted buffer with respect to the tri-state inverter, and what is that? Right, by adding an additional metal line in the layout, of course there will be some kind of a it will become a little bit costly in terms of fabricating the inverted buffer design. But with that, what are we trying to gain? Right, so if we have this kind of a short circuit, and let's say that the D is 1 here, D is 1 means I will have the NMOS to be on, PMOS to be off, phi bar is 0 and phi is 1, that means we have this to be on and on, right? Then I will have this particular 4 transistors. Because this is an off transistor, I can draw an equivalent circuit with only 3 transistors where phi and phi bar now are actually in parallel with respect to Y node and X node. With respect to Y and X, it is in parallel. This X node will be in series with that of the on transistor, the NMOS on transistor, which is connected to the ground. So this is an on transistor, this is an on transistor, and then this is an on transistor, right? And if I want to find out the switching resistance here and then eventually find out the logical effort, right? So the switching resistance here is from the Y to the ground here turns out to be nothing but this two resistance, this two transistor switching resistance in parallel with that of series of this particular transistor. Right, so the switching resistance will be lower in the inverted buffer than when we compare with the Tristate inverter, because in the Tristate inverter I don't have this connection, right? I don't have this X1 and X2 node to be connected by a short circuit or a wire. So I will not have these two transistors in parallel. Having a parallel transistor with a similar width is likely to reduce the switching resistance, the overall switching resistance from Y to ground. So if I have a switching resistance to be lower, then I will have the delay to be low, right? Whereas in an R effective, the R effective switching resistance, switching resistance in a Tristate inverter, it turns out to be nothing but one of them output node, one of them to be used for the switching resistance, and then the other one, this particular transistor. So for the falling down switching resistance, it will be this, and then this switching resistance of this followed by switching resistance of this. Right, so that is what it will be. Here in the inverted buffer, I will have a parallel component which will further reduce than that of the R5 switching resistance. Right, so let's try to quantify that effect. So let's have the width here of 4422. So that is what the width I have. And if that is the width, then for the inverted buffer design, that means that these nodes are connected. And I'm going to evaluate this overall switching resistance, especially if I'm taking this particular case, when D is equal to 1, I will have the falling switching resistance. So the falling switching resistance turns out to be nothing but this resistance on the NMOS side with the size of 2 in parallel with the PMOS transistor of size of 4 in series with that of the D transistor which is on the NMOS side with a size of 2 and then connected to the ground. So here the size of 2 will give me a resistance of R by 2. A size of 4 on the PMOS side is going to give me a resistance of R by 2. So I will have R by 2 and parallel with R by 2 giving me R by 4. In series with R by 2, so I will get 3R by 4. If I have a 3R by 4 for this particular circuit design, what should be my benchmark inverter? So 3R by 4 is going to give me a current of 4 by 3I. So I need a benchmark inverter which will give me 4 by 3I. So my benchmark inverter, just to find out the logical effort, it will be nothing but an inverter. So I'm drawing an inverter wherein the falling current should be 4 by 3I and the rising should also be 4 by 3I. So my width of the benchmark inverter will be 8 by 3 and 4 by 3. Now if I have the benchmark inverter, I should be able to find out what is the logical effort for the D input. So for the D input, it turns out that the logical effort is 2 plus 4, the input capacitance at the D input, divided by the 8 by 3 plus 4 by 3, turns out to be nothing but 12 by 3, which is 4. So I'll get the logical effort of D signal as 3 by 2 in the inverted buffer design. Right, hope this is clear. For the Tristate inverter having the same width of 4, 4, 2 and 2, the logical effort for the D signal turns out to be 4 and 2, and my inverted buffer design is actually 2:1. So the inverted buffer, or rather inverter benchmark inverter is actually 2:1, right? Because my falling resistance is R, which will give me a current of I. So I will have 2:1 inverter as the benchmark inverter. So I will have the total, the logical effort of the D input is 4 plus 2 divided by 3, which is 2. So the logical effort of the Tristate inverter is greater than that of the logical effort of the inverted buffer. Inverted buffer, just going to the previous slide, it is going to give me a logical effort of 1.5. Right here, the logical effort is 2. So the logical effort is more in the sense what happens is the overall delay will be higher for the Tristate inverter. But of course, I don't have to join the metal line in the layout, and also that reduces to some extent the cost of the design. All right. So let's use that particular Tristate inverter in our design. And how do we use it? For a CMOS latch with the output feedback. So we have seen this particular transmission gate and then the inverter, right? And then the disadvantage of this, the transmission gate with that of the inverter was this output node was to be in a floating mode or a it was dynamic. So due to the subthreshold leakage current, this X node will be dropped. The node voltages at the X node will be dropped, and it will have an effect on the Q bar signal. Right now, what if I have some kind of a feedback path, wherein in the feedback path a tri-state inverter is applied and then connected to the X node. Remember that in our previous case, X was supposed to be floating node, and X was floating, and it used to this particular X node, the voltage at the X node used to get dropped due to the subthreshold leakage current when it was in an opaque mode. Right, when it was in when it was supposed to retain the output node voltage for a longer duration, due to the subthreshold leakage current, we analyzed or realized that the X node can get dropped. Now, what if I design a tri-state inverter such that it will drive the X node, especially in an opaque state, right? Especially when the latch is working in an opaque state. So this part of the circuit should be operating in the opaque state, right? That means that I need to have a tri-state inverter here, which will be working, right? Working in the sense that based on the input, I'll get the output to be driven by either by the VDD rail or to the ground rail, depending on the input here. So, but the clock at that level should ensure that the PMOS and NMOS transistor that is connected to the clock, the transistors of PMOS and NMOS that is connected to the clock, right, will turn on those two transistors. Right, and that is possible in an opaque mode, especially if I design this latch with a clock level high, right? So this high level clock is when the latch will be working in a transparent state. That means the output will follow the input. This particular low level of the clock is when we say that it is in opaque mode and the output should retain whatever was the previous state. Right. So in this design, what we are saying is this particular tri-state inverter with the clock should ensure that we supply the clock of the low level signal. Right. So a low level clock should be supplied such that the transistor will be on, and the output, output here will be nothing but the inverted output of the input. Right. And that is the reason why for the tri-state inverter here, the inverted of the clock that is being supplied for the latch signal. So for the latch signal, I have a clock of 5, right? That means that the high level, it should pass the signal. The tri-state inverter is there here, which ensures that the low level clock signal is supplied to the tri-state inverter so that we will have the the complement of this particular input at the output side during the low level of the clock. And that's why a complement of the clock signal is provided to this particular tri-state inverter, right? So if you notice the tri-state inverter, we had the input like this and output like this, and then we had a NMOS and PMOS as 5 bar, right? What it means is the NMOS side we are giving a clock, we are giving a signal of 5, and then on the PMOS side it is the signal of 5 bar, right? But for our design of the CMOS latch, and especially to staticize, especially to avoid the dynamic or the floating node voltage at the X node, right? What we are doing is we are providing the clock signal on the NMOS side, it should be 5 bar, and on the PMOS side, it should be the complement of 5 bar, which will be nothing but 5. So this is what the schematic looks like for the tri-state inverter. So the tri-state inverter, so this will be the Q bar signal. So this will be the Q bar signal. And the clock is nothing but 5 bar given to the NMOS, and then 5 given to the PMOS. And the output is nothing but the X node. Now what it does is, based on the Q bar signal, if the Q bar is 0 here, the output of here it will be 1, right? Even if it wants to drop due to the subthreshold leakage current, this 0 will ensure that the VDD is driving this particular X node or whatever is the capacitance at the X node. So even if I will have some kind of a threshold, subthreshold leakage current in terms of nanoamperes, the VDD is going to pump in more current, and it is going to stay at a logic level of 1. right? And similarly, if Q bar is actually 1 instead of 0, so I will have an output of 0, and then this X node will be driven by the ground rail. So the ground rail is this, and then the VDD rail is this. So that is the advantage of having a feedback path wherein a tri-state inverter is used in the feedback. So thereby making the output node, staticized, or rather it is driven to either a logic 1 or 0, even if there is a drop in the or rather, the subthreshold leakage current is likely to discharge or charge this output node. But because of this tri-state inverter, the rail voltages are going to dominate or drive this X node. So it is no longer a dynamic or a floating node anymore. So this particular design technique helps to overcome the dynamic node voltage at the X node, the dynamic node voltage problem. And just to summarize, when phi is equal to 1, we will have the transmission gate which will be passing, or which will be on, and which will be passing the input to the X node and then to the Q bar output. So it works like a transparent mode or a transparent operation. And the tri-state inverter will be off. So during the transparent stage, the transmission gate is going to pass the signal, whereas the tri-state, because the phi is equal to 1, that means phi is equal to 1 means phi bar is equal to 0. This NMOS and PMOS transistor will be off. So the tri-state inverter will not be on, or it will be off, right? So the tri-state inverter is required only in the opaque state. So when phi is equal to 0, that is when the opaque state starts, and then the transmission gate, it will not pass because this will be 0. And we will have the tri-state inverter passing the signal of the previous output, and with ensuring that the X is retained to the previous X value, right? So the tri-state inverter will be on and Q bar is staticized. So this particular latch design, it is still, this particular at the input side, there is no inverter, so it is still sensitive to the input noise. And the one more disadvantages, which this particular feedback path will bring in is it reintroduces. So this is the output node, and any kind of coupling, noise coupled to the output node is kind of reintroduced back to the X node, especially when this tri-state inverter is on. That is when the opaque operation of the latch is on, right? So it reintroduces the noise from the output to the X node, right? So that is the one disadvantages this particular design brings in. Right. So CMOS latch with the output feedback and the input inverter. So if I bring in an inverter at the input side, then it becomes insensitive to the input noise. So the output is staticized because of this, the feedback tri-state inverter. Insensitive to the input noise because of this particular inverter. But it reintroduces, the noise which is coupled at the output node back to the X node, especially when the tri-state inverter is on during the opaque mode. Right, during the clock level going low. So what to do that? So here is the design. So there is an inverter here, there is an inverter here, there is a tri-state inverter in the feedback path, and then there is one more inverter here which says that this is the output node, and everything else, apart from the output and then the input, everything else is encapsulated or insulated completely. So even if, the Q is getting isolated from the X node, so even if there is a noise at the Q point, because it is freely available at to the outside chip design, even if there is a noise signal that gets coupled into this particular node, it doesn't get reintroduced into the X node because of this particular inverter. And the input noise doesn't get coupled because of this particular inverter. And because of this feedback path, the tri-state inverter, during the opaque state or during the clock's level low, this X node is maintaining the previous X value, right? And this particular design is considered to be the most recommended latch design, especially it is used in the standard cell library, including the Artisan cell library. So this is this is the most standard cell library one can see for a latch design. So once you go into any kind of a design suite, and if you want to pick a latch design, most often you will come across this particular latch design.